In the last three videos, we saw the spectral, polar and singular value decomposition. In this video, we'll discuss an example to understand the working of this decomposition. Let's consider a matrix A equal to 4, 3, 3, 4. And let's find its spectral decomposition such that A can be written as A equal to P, D, P dagger. And since A is real, that is all the entries of A are real, A can be written as A equal to P D P transpose, where P is equal to all the eigenvectors and D is equal to diagonal elements having all the eigenvalues. So let's first find out the eigenvalues of A such that A minus lambda I is equal to 0, which implies 4 minus lambda 3 3 4 minus lambda is equal to 0. So by cross multiplying we have 4 minus lambda minus 9 is equal to 0, and by opening the bracket and multiplying we'll get lambda square minus 8 lambda plus 7 is equal to 0 as the quadratic equation. And solving this quadratic equation, we'll have two values of lambda such that lambda 1 is equal to 1 and lambda 2 is equal to 7. Now let's find the eigenvectors of A. So for lambda 1 is equal to 1, we have the eigenvector v1, which is v11 v12 column matrix, such that A minus lambda I times v1 will be equal to 0. So it implies 4 minus lambda 1, which is 1. So 4 minus 1, 3, 3, 4 minus 1 times v1 vector equal to 0. So we have 3, 3, 3, 3 times v11 v12 equal to 0, which implies we have 311 plus 312 equal to 0, which gives us v11 equal to minus v12. So if we take v11 equal to k, then v12 will be minus k. So we have v1 equal to k minus k. Now let's normalize this vector v1 such that the normalization condition is given by v1 equal to 1. Therefore we have k minus k row matrix into k minus k column matrix is equal to 1. So which will give us k square plus k square equal to 1, which implies k will be equal to 1 by root 2. So our normalized v1 eigenvector is v1 equal to 1 by root 2 1 minus 1. Similarly, we can find lambda 2 equal to 7, the corresponding eigenvector v2, which will be equal to v21 v22 equal to 1 by root 2 1 1, solving in the same fashion. So we can write matrix P, which is equal to v1 v2 as 1 by root 2 1 minus 1 1 1, and P dagger equal to 1 by root 2 1 minus 1 1 1. Also the diagonal vector D equal to lambda 1 0 0 lambda 2, which would be equal to 1 0 0 7. Therefore the spectral decomposition of A, which is equal to P D P dagger, will be equal to 1 by root 2 and 1 by root 2 will be 1 by 2 1 1 minus 1 1 times 1007 into 1 minus 1 1 1. So this is the spectral decomposition of the matrix A. We could also write A in the outer product representation as A equal to summation I lambda I vi times vi, which would give us for this case A equal to lambda 1 v1 v1 plus lambda 2 v2 cat v2 bra. writing the matrix in this notation helps us to calculate its square root and logarithm, such that if you want to find root of A and we have written the matrix in its spectral decomposition, so root of A would be equal to summation I root of lambda I Vi times Vi. Similarly, if you want to find the log of A, and we have already found the spectral decomposition of A, then log of A would be equal to summation I log of lambda I times Vi Vi. So with the help of the spectral decomposition, it is easier for us to do these operations on a given matrix A. Now let's discuss another example involving the polar decomposition. Let us consider a matrix A equal to 1 0 1 1, and let's find its polar decomposition such that A can be written as the matrix multiplication of two matrix U and J, where U is a unitary matrix and J is a positive matrix, such that J is equal to root of A dagger A. So first of all, let's find out J, for which we need to find out the root of A dagger A. So A dagger A would be equal to 1 0 1 1 times 1 0 1 1, which would be equal to, by doing the matrix multiplication, 2 1 1 1. And in order to find out the square root of A dagger A, we need to find the spectral decomposition of A dagger A, as we saw here. So let's find the spectral decomposition of A dagger A matrix so that we can find its root. So the eigenvalue of A dagger A can be found out by A dagger A minus lambda I equal to 0 by solving this determinant, which will give us 2 minus lambda 1 1 1 minus lambda equal to 0, which is 2 minus lambda 1 minus lambda minus 1 equal to 0. Solving this, we get lambda square minus 3 lambda plus 1 equal to 0 quadratic equation. And on solving this quadratic equation, we get two eigenvalues, that is lambda 1 equal to 3 plus root 5 by 2 and lambda 2 equal to 3 minus root 5 by 2. Now the eigenvector v1 corresponding to lambda 1 is v1 equal to v11 v12, which we can find by solving this equation, which gives us 2 minus 3 plus root 5 by 2 for lambda 1 eigenvalue 1 1 1 minus 3 plus root 5 by 2 times v1 is v11 v12 equal to 0. So by multiplying v11 and v12, we get v11 equal to 1 plus root 5 by 2 times v12. So if v12 is equal to k, then v11 will be equal to 1 plus root 5 by 2 times k. Now using the normalization condition for v1 vector, we have 1 plus root 5 by 2 times k into k into 1 plus root 5 k times 2 upon k equal to 1, and solving this we get k equal to 2 by root under 10 plus 2 root 5, and putting this value in v1, we get v1 equal to 1 by root under 10 plus 2 root 5 into column vector 1 plus root 5 and 2. And similarly, if we solve for lambda 2, which is 3 minus root 5 by 2, we get v2 eigenvector equal to 1 by root under 10 minus 2 root 5 1 minus root 5 by 2. Therefore, the spectral decomposition of A dagger A is written as A dagger A equal to lambda 1 v1 times v1 plus lambda 2 v2 times v2. And since we need to find out j, which is equal to root under a dagger a. This would be equal to root under lambda 1 v1 times v1 plus root under lambda 2 v2 times v2, which by putting all these value of lambda 1, lambda 2, v1 and v2, we get j equal to root under 3 plus root 5 by 2 into v1, which is equal to 1 by 10 plus 2 root 5 times 1 plus root 5 2 into 1 plus root 5 2 plus root under 3 minus root 5 by 2 into 1 by 10 minus 2 root 5 into 1 minus root 5 2 and 1 minus root 5 2. Now multiplying these terms and the matrices and adding them, we will eventually get j is equal to 1 by root 5 3 1 1 2. So this is the value of j. Now in order to find u, we have a equal to uj, which implies u would be unique for a and j such that u would be equal to a j inverse. So we have already found j, and in order to find u, we need to find j inverse. We have j given by this matrix, so we know j into j inverse will be equal to I. Therefore 1 by root 5 3 1 1 2 into j inverse will be equal to 1 0 0 1. By doing the row transformation, that is R2 transform into 3R2 minus R1, we'll have 1 by root 5 times 3105 j inverse equal to 1 0 minus 1 3. Similarly, doing transformation on R1, we have R1 transforms to 5R1 minus R2, which would give us 1 by root 5 15005 j inverse equal to 6 minus 3 minus 1 3, which by simplifying we'll get 5 by root 5 3001 j inverse equal to 6 minus 3 minus 1 3. And finally R1 transforms to 1 by 3 R1, we get 5 by root 5 will be root 5 1001 j inverse equal to 2 minus 1 minus 1 3. So this is our identity matrix, which implies root 5 when goes there, we'll have j inverse equal to 1 by root 5 2 minus 1 minus 1 3. So using this we can find u such that u would be equal to a, which is equal to 1011, and j inverse, which is equal to 1 by root 5 2 minus 1 minus 1 3, and multiplying this we'll get u equal to 1 by root 5 2 minus 1 1 2. So therefore now finally we can write the polar decomposition of a, that is a equal to uj, as a equal to 1 by root 5 2 minus 1 1 2 into 1 by root 5 3 1 1 2. So this was the polar decomposition of a. Specifically, this was the left polar decomposition. Similarly, we can find the right polar decomposition a equal to ku, where k is equal to root under a dagger. By finding the value of a dagger and taking the square root of that, we will find k and similarly u, and we can represent a in the right polar decomposition. So I hope you understood the working of these matrix decompositions.